Let's look over the role of the transport layer using these Netacad slides as our guides. So the transport layer is responsible for, as it says here, establishing a temporary communication session between applications. So we're connecting the application layer up here. Now this is our TCP/IP model where we're only in 4 layers. So the top 3 layers of OSI over here, session, presentation, and application, all become one big application layer in TCP/IP. So you might recall layer 3, IP, it's a best effort delivery. In other words, those packets are going to get sent to their destination, whether that destination is there to receive them or not. So there's no real control. There's no verification that those packets are going to make it there. That's what we do here at the transport layer, at layer 4. So TCP is ultimately responsible for that. UDP can do some similar things as well. So the first thing we're going to look at, tracking individual conversations. So if you're on your home network and you've got, here's your cell phone over here, you've got several web pages, maybe you're playing a video game, there could be several things happening on your network all at the same time, and your router needs to take care of that. Your router needs to keep track of which messages go to which thing. Similarly, your own computer might be doing that. So you have a single IP address on your computer, a single MAC address on your computer, and it might be handling a dozen websites simultaneously while also having a chat application and doing email and any number of other things. So we have to keep all of those separate conversations separate. So that's one thing that happens at layer 4, is keeping all of those different services in their own lane. We also have segmentation. We've talked about segmentation a lot. So if we are going through our encapsulation step, right, you have data up here, and maybe it's a big block of data, it's a huge download. Well, we can't just send that entire download all at once. Think about a game of telephone like we did in our earlier assignment. What if you wanted to read an entire book via a game of telephone? How would you do that? You'd have to break it down into smaller chunks. So what we would do is maybe read one sentence to the person next to you, and when that one got all the way to the end, you'd read the next sentence. It would take forever, but that's the only way you could do it. So what we do is we chunk our data, and we send each piece of that, a few bits at a time, down the wire. So we're going to send the D, then the A, then the T, then the A, and hopefully all of those get there, that we even have methods of making sure they do. And then the last bit here at layer 4, identifying the applications. And so this is, we do this via sockets, via socket pairs, in fact. So you might have one web page that you go out and request from a web server, and you request that on a certain port, probably port 80 if it's HTTP, or 443 if it's HTTPS. But you might be doing multiple web pages to multiple servers. So each outgoing connection gets a port as well. So when it responds, it goes back to the correct port. I think that's over here at layer 3. There we go. And so you can see what they've done here is just give some different shapes to identify the traffic going to these different applications, all on the same computer. Now, when we come out of our router to our computer, and we have the web pages and the streaming and the video games, all of that data is mixed up together. So it's not just that we have all of the web page load over that line and then the next thing happens, right? And then all of the chat and the next thing happens. In fact, all of those packets are interwoven together. So we get a couple of web page packets over here and a couple over here and a couple of chat messages over here. And then, Netflix plays a couple of frames. And it all gets mixed together. And this is called multiplexing, also known as muxing. So multiplexing just means we mix all of the data together, and then when it gets to the destination, we have to figure out where it goes. And that's what happens on the transport layer, is figuring that stuff out. Now, I mentioned that IP does not offer any reliability because it's a best effort. That's where TCP comes in. So the way TCP works is it has a little conversation with the recipient, and it goes a little something like this. So here you have your sender, and you're sending to a recipient. So here we send, here we receive. And if we have a large hunk of data over here, we segment it first and we send the segments across the way. But how do we ensure they actually get there? What we're going to do is we're going to ask our receiver for a response. We're going to say, hey, when you get this data, let me know. And we're going to speed up as we do this. So what we're going to do is send one packet, and that one packet gets sent, and we receive one packet. And the responder says, hey, I got one packet. Cool, that's great. We're working out well. Now I'm going to send packets 2 and 3. I'm going to speed up a little bit. I'm not going to just send 1 and wait for a response. I'm going to send 2 and wait for a response. So those 2 get sent over, and it says, hey, I got packet number 3. Notice I don't say 2 and 3. I just say the last one I got. So this is my count. All right, good. I'm going to speed up a little more. Here's 4, 5, and 6. I got packet 6. All right, everything's still going well. Here's 7, 8, 9, 10. Now I'm sending 4 packets. Got 9. Uh-oh, we've got a problem now. I sent 7, 8, 9, 10, so I've sent 4 new packets, and my total count should be 10. The respondent said my total count is currently at 9. We dropped one of these. Now, we know that we were good here. We were okay at 6, so we don't have to start over at 1. We don't have to send everything. But we don't know which of these 4 packets over here was the one that got lost. So what we're going to do is we're going to wipe these out. We're going to inform our recipient, hey, that didn't work. Let's try again. Here's 7 and 8. We're going to slow it down. Send those across. I'm now at 8. Hey, we're good. And we just go back and forth like that, managing the speed in this manner, but also verifying that all of our packets get to the end because our recipient is telling us, hey, we are good up to this many packets. So that's how TCP can verify that the data has gotten there reliably. It acknowledges the received data. It tracks the number of segments sent, and that's how it does the acknowledges. And then it retransmits any that it didn't get an acknowledgement for. Notice it also says after a certain period of time if they're unacknowledged. So we might send packets 7 and 8, and nothing happens. We don't get a response. So we're going to wait and wait and wait. And eventually we're going to say, all right, I'm going to give up. Here's 7 and 8 again. And we're just going to resend those after a certain timeout. Now, UDP is TCP's faster cousin, and UDP does the same job but differently. So with TCP, we use it when we need reliability. If we're going to download something, that download has to be complete. If we're going to download Steam, we have to get every bit of that before it's going to install correctly. But some applications, we care more about speed. Let's say that you're watching Netflix, or you're watching a live stream. You're going to watch a Twitch stream. So if you're watching a live stream and we drop a frame, no big deal. We just keep moving, right? It would be better to drop a frame and keep caught up than it would be to pause and wait for buffering and then keep going again. Or think about a telephone call. If we're on a telephone call with somebody, voice over IP, and we accidentally miss a syllable, we probably still understand what they said. Better that than to resend 20 packets all at once or have all of these hiccups that occur that TCP would have. So TCP rewards reliability, whereas UDP rewards speed. So with UDP, it's okay to lose data. Sometimes it's okay to lose data. What we care about is that the data just keeps flowing faster and faster and faster. So there's UDP, you see streaming live video and IP telephony versus TCP. It shows SMTP and POP here for email. For the most part, you don't see a lot of those these days because we're checking email through the web page, through Gmail or something like that, over HTTP. So these two protocols sort of work together, TCP and UDP, for different purposes. So that's an overview of what happens at the transport layer. Next, we'll get into these things with a little more detail.